It's great to have you here, and I'm honored to present ACRN with regard to functional safety design and the certification plan in today's session. Okay, so here's the outline. So today in this session, we will cover these four aspects. So first, we will talk about the high-level safety concept, how we assume that the ACRN hypervisor will be integrated in a safety-related system, and how ACRN can help consolidating multiple workloads with with mixed criticality and um, establish freedom from interference between the safe and non-safe parts. And based on that, we'll talk about two safety-related aspects. One is how ACRN is being developed and what are the techniques that are adopted during the development to avoid bugs, or using terms from the functional safety standards to avoid systematic faults in the implementation. And the second part is about the mitigations to interference, or to be complete, it is first an analysis of potential interference modes, some of which can be mitigated by adopting some technologies inside the hypervisor, while there will be some residual interference mode that needs system level mitigations, which we will highlight in the section as well. And finally, we will talk about the current certification plan, how we plan to talk with third-party certification body, or to be precise, to suit, to assess the current concept and work product we have generated, and what's the current status. So, and finally, we will come to the conclusions. So first, about the safety concept. Just 1 or 2 hours ago, Jason has introduced that. So for the mainline ACRN, we have a lot of, not a lot, but a few modes, a few different modes, depending on how the different VMs are deployed and launched. So in a safety critical usage, we assume that all the VMs are pre-launched, which means every VM is launched by the hypervisor directly, not by another VM. And the hardware resources allocated to each of the VM are explicit. Not like where we have the service OS where all the hardware resources are available, if not allocated to any pre-launch VM, will go to the service OS by default. And this includes not only PCI devices, but also ACPI registers, ACPI device objects, and other kinds of platform-wide devices, which could lead to safety concerns, especially from interference perspective. So the safety concept, as I just explained, is the so-called partition mode, where we partition the hardware resource into two parts. One is safety related, where you can have a safety VM running safety related workloads like your periodic checks and safety critical like calculation and other kind of tasks. While on the other cores, you can have the non-safety related VM, where you can deploy standard RT stacks like codices, and you can have your EtherCAT communication stack, for example, and you can deploy other kind of stack as you wish, as long as the hardware resource can afford it. So they are mixed criticality. So as a result, the hypervisor itself is in charge of avoiding or mitigating interference of the non-safety part on the safety part. So as a basic design principle, we allocate hardware resources, including the processors and memory, in a static way. So all the allocation is statically defined and configured at startup time. So there is no runtime resource balancing or other kind of things, which could give complexity to the analysis of deterministic timing and other aspects from safety perspective. So the target as the SC or the systematic capability of the hypervisor is SC3, which should be able to be integrated in a system requiring CO3. And the scope of our certification is, of course, the hypervisor itself. So the hypervisor interacts with both VMs, interact with the hardware, and it is part of the safety-related part, which needs to be certified either by Intel or by OEM, ODM, or customers. So this is the overall concept, and to to justify that Acorn is suitable to be used and fulfills the systematic capability 3, we need to have a systematic development model and advanced techniques applied in the development to justify that the probability of having systematic faults or bugs inside the hypervisor implementation is low. It's low enough. So a quick look at the developed model, which is a very typical V model. So from the market requirements or from the assumed safety concept, which we have defined earlier, we start the requirement analysis, architecture, module design. All of these are work products, or also representing phases where we generate work products, including the requirement specification or the architecture design specification themselves, as well as the review evidences as is required by the review process specified by the functional safety standards. And all of them are one derived from from another, and the correctness, completeness, and consistency are checked during the review or verification process. And this comes down to the implementation or the code part. And at the same time, we also have this planned multiple levels of test campaigns to verify the implementation from different in different ways. One is the module test, where we exercise each function in the implementation separately using existing unit test frameworks. And we also statically scan the code to identify potential coding violations to common coding guidelines. And at integration level, we integrate the different modules of the Acorn hypervisor one after another, exercising the external interfaces, inspecting its behavior and its interaction with among these modules to make sure that they are correctly implemented and there is no unintended behavior. And at this level, we also integrate the software hypervisor onto the hardware to exercise it on real hardware to check the behavior, whether it is expected. And we also inject faults into the hypervisor to check whether it can catch faults as has been designed by the software architecture design specification. And at the a third level of verification activity we have planned is the validation, which is also implemented mostly using tests. So in the validation tests, have the hypervisor integrated as a whole hypervisor and acts like a VM running up on top of the hypervisor, so that it exercises the different CPU features or past devices that has been passed through, or other aspects that the hypervisor provides, and make sure that the behavior of instructions or devices from VM perspective is correct with regard to the requirements. And the requirements themselves are mostly derived from the SDM, or the Intel Software Developers Manual, which specifies the hardware behavior. So this is the complete development model, including the verification activities. And to support the execution of these phases, there are also a bunch of supporting processes in place, including how documentations are managed, including documentation IDs and version control, and how requirements are managed, especially how requirements are fulfilled by establishing bidirectional traceability, and calculating traceability coverage to make sure that all requirements or all design aspects has been implemented, and or, for example, design are derived from requirements. And the general verification process to specify what is generally required for a verification activity, including reviews and tests. And also the change management and configuration management to manage different versions and to manage changes between these versions to make sure that the impact of changes are properly analyzed and changes are implemented in a consistent way. Also, as is required by the functional safety standards, we also classify and qualify the software tools we use during the development model. So this is, from process perspective, how we increase the confidence that the systematic faults inside the hypervisor are properly detected during the development, so that the output implementation can be used in safety critical usages. So in addition to the development model, another important aspects from the functional safety standards to avoid systematic faults is to apply certain techniques. So in this page, I will list out some major techniques we apply during the development to list out what are so how we increase the confidence in general. So the first category, including the semi-formal notations and bidirectional traceability, are commonly used at the left side of the V model, including the requirement management, architecture design, and module design, to make sure that first we specify the requirements, we specify the design in using semi-formal notation so that the syntax of the documentation is properly defined to avoid ambiguity and make the document concise and precise to read. Also, the bidirectional traceability is established among these work products for coverage evaluation. And the second category is about how the hypervisor is designed. So this includes the event-driven architecture, which is quite natural considering how the hardware virtualization extension works on Intel architecture. And we also apply modular design by decomposing the whole hypervisor as a software element into multiple components and further modules. And we have applied restrictions on module size to make sure that this decomposition really makes sense. So we do not have a module which covers half of the code, which is definitely not good for managing complexity. So from the implementation and module test perspective, we have defined our own coding guideline and using third-party stat analyzers to review the code so that the violations to the guidelines are reported, and either these violations are justified in case we really need some, for example, type conversions or other seemingly error-prone operations, but which are typically required for a system software like a hypervisor. But or these violations are really true violations, and we need to fix the code to make sure that we use the C language in a safe way. Also, for the dynamic test, the module test, which is implemented mostly using unit tests, we evaluate the structural coverage to make sure that the module test itself has exercised the statements, the functions, and especially the branches in the implementation, so that all the expected behaviors are exercised and we do not have unexpected behavior, which in most cases will lead to unvisited branches in the dynamic module test. And finally, we will also, of course, have the failure mode and effects analysis, which is a qualitative analysis based on keywords like hazard, to identify potential issues when we expose certain features to the VMs from functional and interference perspective. So we also listed the impact from functional side because we, as a hypervisor, we have no idea how the safety VM will use the CPU features the hypervisor provides to it. So all the features is maybe potentially be safety related if the safety related workloads uses a specific feature. So so from this consideration, we analyzed all the features exposed to gas and identify potential issues that can arise and identify the mitigations or preventions or mitigations. And if additional mechanism is required to be implemented inside a hypervisor as a mitigation, then we feed that back into our requirement specification or architecture design and make sure that it is properly implemented and validated using fault injection tests. Or if it derives a, for example, assumption of use, then the assumption of uses will be properly recorded in the safety manual for customers' reference. As I just mentioned, the fault injection test is also planned to exercise the hypervisor under abnormal case situations, including the failures that has been identified by the failure mode and effect analysis, as well as some other common errors identified by our QA team during the error guessing process. So all these are techniques we have applied on ACRN hypervisor to make the hypervisor not work, but also work in a deterministic and accurate way. Okay, so much about avoidance of systematic faults. And then let's talk about at the requirement and design phase, how we systematically specify the hypervisor so that we can achieve deterministic behavior from external software component perspective. At the requirement analysis phase, we have categorized the requirements into different aspects, including the functional requirements, the safety and security related requirements. And at the requirement analysis side, we also derive some assumption views we have identified at that stage. So for the functional requirements, as a hypervisor, the typical way of thinking what a hypervisor should do is using so-called small step semantics by thinking about what's the initial state as a machine of the VM the hypervisor prepares, and what's the behavior of certain instructions that in a vCPU, in a virtual CPU, that so what's the behavior of such instruction, and the boot sequence, so how the whole machine starts up. So that's how the functional requirements are categorized into the virtual CPU capabilities derived by enumerating the features listed in the software developer's manual and analyze one by one. And specify the VM boot sequence. So how different VMs are to be started, and what's the timing sequence, and whether there is any ordering between the launch, as well as how the hypervisor initializes itself before launching any VM. And also, a third equally important part is the initial states. So this includes the initial states in the registers, the initial states in memory, the initial states of the pass-through devices. All these will impact the behavior in the guest if there are some undefined or unspecified values in these registers, but these registers impact the behavior of guest in a certain way. So in the requirement analysis phase, we have make all these details explicit to make sure that the behavior of the hypervisor is explicit and precise. So with regard to the safety and security requirements, one or maybe the most important safety-related part of a hypervisor is to mitigate interference. And also, equally important from security perspective, the hypervisor is also responsible for mitigating some side channel vulnerability, and these are listed as the requirements to ACRN explicitly as well. Talking about assumption of use, this mostly include hardware capabilities. Some mitigations requires certain hardware extensions, which is a very typical and or maybe mostly um, required way to implement interference mitigations according to the ISO 26262 standard. And also, in addition to the mitigations we have applied, there are also some assumptions on what kind of system level mitigations that will exist in the integrated system. So this is mostly to mitigate temporal interference, which we will talk about in a minute. Talking about this architecture design, again, we decompose the architecture design into three different aspects. One is the initialization phase. So the hypervisor initializes itself, how the hypervisor initializes the VMs, and the runtime, where we have the event-driven architecture. So the hypervisor does nothing but reacts to certain VM access triggered by VMs. And a third part is how to mitigate errors. So for the initialization, this includes how the hypervisor initializes hardware resources and allocate hardware resources, of course, and how the hypervisor initializes itself, especially the internal data which represents different VMs, and how the hypervisor initializes the hardware virtualization extension to determine what kind of runtime events will be triggered to allow the hypervisor to do some emulation or interception. And once all these initializations are set, then we come to the runtime or the operational mode, where the hypervisor only handles VM access. And the behavior of each VM access is, of course, precisely defined as part of the architecture design. And for the error mitigation, of course, we need to decide two aspects. One is what kind of errors we need to detect and how to detect them. And after being detected, how these errors are to be handled. So some of them can be, yeah, I don't want to say ignore, but depending on the nature of the error, some errors are reported when the hardware has already blocked these, for example, invalid accesses. So there is no further impact to safety. But in other cases, there could be potential safety impacts where the hypervisor needs to take further actions, like shutting down the non-safety VM if it is trying to do some malicious things. And in addition to these high-level parts, the architecture design also is responsible for decomposing the hypervisor into different modules and define the interface of each module and how they interact with each other. All right, so much about these systematic process and the requirement analysis and architecture design. Then let's talk about interference. So the typical inter-VM interference modes, where we have the idea is borrowed from the Kobata et al.'s work in 2013, where they listed a checklist or a reference list of potential interference in a multi-core system. So generally, interference can be divided into two categories. One is spatial, the other is temporal. Maybe I need to zoom in a bit. So the spatial interference mostly includes two cases. One is that the safety VM, or the non-safety VM directly access the memory that has been allocated to a safety VM. And the other is that it does not directly corrupt them, but it programs a device allocated to it to conduct a DMA transaction to corrupt the safety the safety memory. So this is the first category, and the temporal category. There are more cases. One is that the local cache are to make local cache coherent. The hardware has some traffic, some internal traffic among the local caches of different cores to make sure that invalidated cache lines are populated before they are accessed on a different core. And sorry, and the second, so as for the shared cache and the shared memory controller, which are typically the memory controller is shared because all the cores on the physical platform can access to it. So the non-safety VM may be conducting some atomic operations, which will lock the shared cache or the memory controller, and this could lead to non-deterministic latency when the safety VM tries to access the shared cache at the same time. So the third is about the non-safety VM not locking the shared cache or memory or the peripheral bus, but sending a lot of transactions so that there is some kind of traffic jam on these shared buses, and the safety VM cannot access the shared resource in a timely manner.
Junjie?
The fourth is that, sorry, yeah.
Yeah, this is Jeffrey here. You have about just a little under 10 minutes left.
Okay. Okay. There are only 2 or 3 pages.
Yeah.
If I conclude.
Thanks.
And the fourth is that the non-safety VM tries to evict cache lines that has been used by the safety VM to cause additional memory access latency for the safety VM. And the fifth is that the non-safety VM programs a device to deliver interrupt to a safety VM. So from safety VM side, it receives not malicious, but spurious interrupts, which it cannot handle, but at least it has to react to the interrupts. Only after that, it knows that this is spurious and it don't need to take care of it, but interrupt handling itself takes time. So these are the interference modes. And for the spatial interference, it is quite easy because we already have hardware extensions to avoid this. For direct access, we have the extended page table. And for the DMA transactions, we have the IOMMU to block invalid DMA transactions on the safety-related memory from the non-safety side. For the temporal part, what we can do are as follows. So the first, for cache eviction, we have the cache partitioning mechanism, which can be utilized to avoid the non-safety VM evicting a cache line used by the safety VM. So the cache partitioning typically partitions ways of a shared cache so that the safety VM has exclusive access to part of them. And for the interrupt delivery part, we used, again, the IOMMU or the interrupt mapping mechanisms in the IOMMU to avoid the delivery of these interrupts. And for the residual temporal interference, this mostly includes the other cases which we have listed, including the coherency traffic. So considering that the memory is statically allocated and not shared between the 2 VMs, so in theory, there will not be any cache line invalidation or eviction due to the coherency protocol, but the coherency traffic itself still exists, and it will take some of the cycles in the internal buses. And the second, with regard to cache locking and to the shared cache locking and the traffic jam, of course, additional hardware mechanism is required to properly detect and avoid and mitigate these issues. But at least we can assume that at system level, we can mitigate this interference from safety perspective by deploying external watchdogs, which are quite which is quite a typical way in safety critical usages. Okay, regarding to the certification plan, we start engaging external certification bodies from, let me recall, maybe it's 2009, somewhere 2019. And in May 2020, we submitted our concept phase work products, including all the planning documents, the requirement specification, architecture design specification, and the VMV plan to TÜV-SÜD. And by June 2020, we have received the technical report from the certification body, stating that the ACRN hypervisor is able to fulfill the requirements according to CO3 of the IEC 61508 standard. And now it is May 2021, and we have mostly completed all the work products, including the test campaigns, of course, the implementation, test campaigns, and the safety case, safety analysis, safety manual, etc. And we plan to submit our second batch of work products soon, and we plan to have the second phase audit in June 2021. All right, some concluding remarks. So from concept perspective, currently we certify ACRN hypervisor in partition mode, which allows the consolidation of mixed critical workloads in the safety critical use cases. And currently the scope covers 2 partitions, but it is straightforward to extend the concept to more than 2 partitions as long as we have sufficient hardware resources. And the second is that to mitigate certain interference, the hypervisor leverages hardware mechanisms. But with this mechanism in place, we also have some residual temporal interference, which needs system level mitigations. And from certification perspective, we are on the way to reach the goal, the final point of the certification. And in case you're interested in the certification package, which is managed by Intel IOTG and available under NDA, you can contact your sales representative for details. So that's all I have today. Any questions?
Thank you, Junjie.
It seems that the chat window is quite busy.
Yes, there were a few questions on the chat window, so I know you've probably not been following them during the presentation, but there were a few of them.
Mm-hmm.
Actually,
Okay,
scroll back up again. I think there was one that's. I think some of them have been answered.
Mm-hmm.
Actually, perhaps if anyone in the audience had a question on the chat window that hasn't been answered, can you perhaps ask it again?
So let me go through the list. So first, about the total lines of code. So currently, the mainline ACRN code, if we exclude the debug code, is around 28 or 29 line of code, and the current certification scope, which is the pure partition mode, covers about half of it. So that's 13 to 14 thousand line of code. Sorry. Okay, so with regard to the second, to develop hardware. So this is not a pure safety-related question, but to emulate hardware, ACRN hypervisor itself may not help that much because the hypervisor is designed to manage and divide hardware resources. But for virtual device emulation, it is the ACRN device model or QEMU's scope. So maybe these virtual devices. I don't think that writing a virtual device is either way simpler because the most complex part is to implement the hardware logic using software by itself, and it has to be done regardless of whether you are using ACRN or whether you are using QEMU. So that's about the pure device part. But if you are using the device mediator, then it is a different story. Trading dependent. How do you diagnose the healthy condition of hardware during runtime? With regard to the diagnostic part, we have the safety VM running periodic diagnostics. This not including not only the hardware mechanisms used by the hypervisor, but also the additional diagnostics required from hardware perspective. So these periodic tests will report to some external IP, which are I would say the root of safety. So if you are talking with IOTG about the concept of safety island or other kind of things, this is the current concept we are implementing at system level. And with regard to the processors supporting cache partitioning or to using Intel terminology, it is a cache allocation technology. You can refer to the CPU ID, which is of course the golden reference. And for manuals, you can also refer to the processor specifications available on Intel official website. And for SIL4, currently we have no plan to certify to SIL4. So that is what I can share as of now. All right, that's all I have walked through the chat list. If you have any further question, kindly let me know.
Hello, I would have a question. When comparing the partition mode with the hybrid mode,
Yeah.
Do I understand it correctly that in the partition mode there will be actually no service OS, so I cannot have like multiple non-safety VMs? Or could I
you
use it?
You can still have multiple non-safety VMs by configuring multiple non-safe pre-launch VMs. So there is no limitation on how many pre-launch VMs you can configure theoretically. Maybe there are some limitations inside the current implementations, but from design perspective, of course you can do that. And if you want to use the hybrid mode, not most maybe not for having multiple VMs, but also have the capability of sharing devices among multiple non-safe VM, then the additional workload you need to do is to understand the impact of the service OS, which, as I have just indicated, owns all hardware resources except that has been allocated to the pre-launch VM. And in our case, it is mostly the pre-launch safety VM. So this includes a lot of model-specific hardware IPs, which manages the whole platform. And in this case, they can have the potential that tweaking certain registers in these IPs will have platform-wide impact, which will also affect the functionality or even the safety-related tasks inside the safety VM. And this needs to be understood, of course, before we use the hybrid mode or the service OS in safety-critical uses.
Okay. One more question from me. Is there guaranteed some compatibility for the VMs for the version which is non-safety certified and which is safety certified? If I would have this is interesting, especially for the non-safe VMs. If I have a non-safe VM which I would also want to migrate or use on the safety certified ACRN, would I be able to use it, or do I have to count with some adaptations needed?
So this is generally a question from the virtual platform definition perspective. So currently the philosophy of ACRN is to expose processor features as much as possible and as much as the hypervisor can. So if the your non-safety OS is not only about the kernel but the whole OS and its applications, uses these or a subset of these hardware features, then of course you can run that. So it is likely that you can run your stack in in a VM without major modifications. But maybe there could be some modification on the configurations depending on the actual OS. But if you are using some features, for example, like power management or other or access specific hardware IP, then we need to analyze case by case whether Acorn currently supports accessing these resources from a VM, and if not, then we need to analyze the gap and identify the additional effort we need to pay.
I see. Okay, thank you.
My pleasure.